Okay. Professor Lemay will tell us about reverse Faà di Bruno formulas for Cartesian.
I can't even see my slides. I'm going to stand right here. Okay, so yes. So first of all, I'd like to dedicate this talk, my second talk of the week, again to Phil Scott. For those of you that weren't there yesterday when I did this dedication, Phil Scott essentially taught me half of my undergrad, and then after that, he became a friend and a tutor and all that good stuff. And so he'll be greatly missed. Phil was really interested in this differential categories things, so much so that he invited Robin, myself, and two of our collaborators to do a special issue for differential categories, which unfortunately he will not see the conclusion of. So yes, so I'd like to dedicate this talk, which is again about, as David just said, reverse Faà di Bruno formula. So maybe you were here for Tyler's talk on Wednesday, where he talked about Cartesian reverse differential categories. So he already motivated the subject, so I don't have to. But I'll do my best to do so anyways. So first off, I'd like to say that this is joint work with Aaron Biggin, who is a great undergrad student. And in fact, the reverse Faà di Bruno formula is actually there on the whiteboard. Spoilers if you want to look at it. If not, here's my next slide. So yes, so there are two types of derivative operations that are used in automatic differentiation. There's the forward mode differentiation and there's the reverse mode differentiation. And forward mode will always be blue and reverse mode will always be red. Don't ask me why. It's just how I see them in my head. And so the forward mode differentiation is captured by Cartesian differential categories. And these have been quite successful in sort of giving the categorical foundations of differentiation and capturing various different things about differentiation. Cartesian reverse differential categories instead give the categorical foundations of reverse mode differentiation. And these are introduced, I guess, in CSL 2020, and they've actually been quite popular, even though they're still in the early stages of development. And they've been able to formalize certain things like some certain gradient descent algorithms, more foundations, some differential programming language stuff, etc. So the idea is that Cartesian differential categories come equipped with a forward differentiation operator. And this is axiomatized by several rules, in particular, the chain rule, which tells you what the derivative of a composition is. On the other hand, Cartesian reverse differential categories, well, as the name suggests, would instead come equipped with a reverse differential operator. And this time also axiomatized by certain axioms, including the reverse chain rule, which tells you what the reverse derivative of a composite is. And so what we think of as the fundamental theorem of reverse differentiation, categorically speaking, is that reverse differentiation equals forward differentiation plus a transpose operation. So the point is that if you have reverse differentiation, I can construct the forward mode derivative. And if I have the forward mode derivative plus a sort of transpose operator, then I can do reverse differentiation. So it's been quite fun to sort of take the theory of forward differentiation that's now well established, add in a transpose operation, and see what you get to get sort of the reverse differential analog of things. So for example, most recently, we've been able to sort of start doing reverse differential geometry, which has been a scary sounding name, but it's been quite fun. But today's story is about giving the reverse differentiation analog of what's called the Faà di Bruno formula. So potentially this is not something you come across in maybe your undergrad, but essentially the Faà di Bruno formula is just the chain rule for higher order differentiation. So the chain rule is the Faà di Bruno formula at level 1. And the Faà di Bruno formula holds in any Cartesian differential category. So today's story is just to give the reverse differential version of the Faà di Bruno formula in a Cartesian reverse differential category. So here's how we're going to get there. So to express the Faà di Bruno formula in a Cartesian differential category, I need to tell you about two things first. I need to tell you about partial differentiation and higher order differentiation. And so if I want to give you the reverse differentiation, the reverse mode differentiation of that, I have to tell you about partial reverse differentiation and higher order reverse differentials, which have not previously been discussed in at least our papers. So Aaron and I sort of developed that in our ACT paper this year. And what's been quite interesting is that these partial reverse differentiation has allowed us to sort of revisit some of the main results in our first introduction paper and sort of give another perspective on some of those key results. And so just jumping ahead to the end of the proof is that the reverse Faà di Bruno formula is essentially then computed as the transpose of the Faà di Bruno formula. So you're applying that transpose operator that you get when reverse equals forward plus transpose. And there you go, there's my talk, I'm done. But now I'll go into details. Okay, so let's go under the hood and let's look at some definitions. So for both the forward mode and the reverse mode differential categories, the underlying category is what's called a Cartesian left K-linear category. So for a commutative semi-ring K, which will be my base ring for the rest of the talk, a left K-linear category is one where all the Hom sets are K modules. So I can add maps together and I have scalar multiplication. However, only composition on this side preserves the K-linear structure. So examples to keep in mind is, for example, polynomials. I can add polynomials together, but not every polynomial is an additive function that preserves K-linear structure. And then a Cartesian left K-linear category is one where the projection maps are K-linear maps. So they do preserve addition and stuff like that. Okay, so a Cartesian differential category, so the forward mode version of this stuff, is a Cartesian left K-linear category, which comes equipped with a differential combinator. And in the literature, we don't call these forward differential combinators, but for today's talk, I will do my best to call these forward differential combinators because we're going to talk about reverse differential combinators in a few slides. So forward differential combinators picks up a map f from A to B and then spits out its derivative, or forward derivative, d of f, from A times A to B. So here, the colors are just there to help us keep track of things. There's nothing special about it. The only thing special is that, look, here's an A, and there's an A in the domain. Here's a B, and there's a B in the codomain. That's it for now. And the forward derivative has to satisfy 7 axioms which capture the essential properties of the derivative from differential calculus. Hello. Okay. And there is a very practical term logic for Cartesian differential categories. So we're going to sort of always write down differential derivatives like so. So this notation is inspired from the notation from differential calculus. So you think of this A as being the point of your derivative, the point input, and B as being the linear vector input of your derivative. And this lower d of x is the variable that's being derived, so it's bounded. So in particular, the chain rule for this derivative tells you how to derive the composite of functions, and it's written as such using the term logic. So as you can see, if we're thinking of this in the one variable case, this is indeed saying that, you know, in some way this dot is somehow multiplication, but not really. But the idea is that this is g prime evaluated at f multiplied by f prime. So this is the formula that hopefully you've come across in Calc 1 or something. Okay, so the main example that we're going to have today is sort of the same example that Tyler used in his talk, is the Leverrier theory of real smooth functions. So this is my category, my objects are Euclidean spaces Rn, and then my maps are just smooth functions between them. And this is a CDC where for every smooth map from Rn to Rm, well, remember that this capital F is actually just the tuple of little smooth functions from Rn to R, then its forward derivative is just what's called the total derivative. So it's the tuple where at each component, it is the sum of the partial derivatives of Fi. So this is, in the first component, it's all about F1, and the last component, it's all about Fn. So in particular, in the special case where I'm just taking a function from Rn to R, then this is really just the sum of the partial derivatives of f. Nope, this way. Okay, now let's go reverse mode. So a Cartesian reverse differential category is this time comes equipped with a reverse differential combinator, which this time picks up any map from A to B and spits out this reverse derivative, where now it's important where you have to keep track of the types of things now. Because look, all of a sudden I had a B in my codomain, And now there's a b that's appearing in my domain. And the a in my domain now appears in my codomain. So this is why I like using colors, because it allows me to keep track of things. And it's called reverse mode because, all of a sudden B, the code, you're sort of inputting an output that you originally had. And again, this is going to satisfy 7 axioms. And so what's really useful, what Aaron and I came up with is a sort of, not exactly a term logic for CRDCs, but what we called a proto-term logic, because we didn't prove any soundness or completion. It really is just there to help us do proofs. So inspired by the term logic in a CDC, we're going to write reverse derivatives as the same sort of notation, but this time using an R's. And so, yes, some of our anonymous referees gave us some other useful notation, but I thought that this notation was sort of, for now, okay, because we just followed what the 4 derivative people were doing. And by people, I mean Robin, who's there. So the reverse chain rule is stated as such. So it's sort of, and the reason it's called reverse chain rule is now when you take the reverse derivative of the composite G composed with F, now F appears on the outside. So this is super important, and then G appears on the inside. So it really is sort of reversing things around. So the canonical example is again the category, the Levier theory of smooth functions. So the reverse derivative of a smooth function from Rn to Rm. This time, look, it's really important. So now the reverse derivative takes in a vector of n variables, n variables first, m variables second, and outputs something in n variables. So this is going to be a tuple, but this time I'm taking the sum over m of all the derivatives in x1 of all the functions. So remember that the forward derivative was the sum of the partial derivatives. This time it's the tuple of the partial derivatives. So now let's review the fundamental theorem, which I claim to say that reverse differentiation was equal to 4 derivatives plus transpose operators. And so the theorem says this exactly. A Cartesian reverse differential category is precisely the same thing as a Cartesian differential category equipped with a contextual linear dagger. So that's just the fancy word to say the transpose operator that I was talking about, which I guess I write in green. And so to help express this, we realized that actually the notion of partial reverse derivatives were quite useful. But first let's review the forward version. So in a Cartesian differential category, how are you going to do partial derivatives? So if I have a function which has inputs a1 to an, I'd like to be able to take the derivative of aj while keeping the other input variables constant. Well, it's okay. I'll just put everything on the slide. The way you do this is by inputting zeros into the total derivatives. And this is the same thing that they do in calculus. To go from the total derivative to partial derivatives, you just put zeros in the right place. So the jth partial forward derivative, where I'm deriving the variable aj, so now I have an extra variable here, aj, that appears, is defined as follows. So now I'm using this notation to just show that I'm only deriving the xj variable, and it's equal to the total derivative where I put zeros everywhere except for the j variable input. And in our example, we saw that, as I said, the total derivative was equal to the sum of partial derivatives, and this is true in a Cartesian differential category. You can make this precise by saying that the total derivative is indeed the sum of all these jth partial derivatives. So let's do this for reverse differentiation. So in a Cartesian reverse differential category, we'd like to do the same thing. I want to be able to take my aj variable and take the reverse derivatives, but so this time I have a b in the domain that appears and an aj in the codomain. Well, how are we going to do this? Well, let's first consider the type of the reverse derivative of this function. There's going to be in the domain, and there's going to be a1 to an in the codomain. So how are we going to get a map that goes all the way to AJ? Well, we have finite products, so we have projections. So therefore, very easily, we define the jth partial reverse derivative as just being the projection of the total derivative of the total reverse derivative, the jth projection, so the jth part of that tuple. And yes, this looks obvious, and I'm not saying it's not. And we do get the nice little lemma that says that, like in the examples where I said that the reverse derivative was the tuple of the partial derivatives, the same is true here. The total reverse derivative is, by definition, because this is the universal property of the product, the tuple of the partial reverse derivatives. Now, the proof is automatic, but something that's quite neat is that for reverse differentiation, this is automatic, but the lemma I showed for forward differentiation, there were some calculations to do there. So that was a neat little mismatch that we observed. And as I mentioned at the start, partial reverse derivatives, while obvious and easy to define, have actually been quite useful when revisiting some of the results in the original paper. So now that I have partial reverse derivatives, it allows me to sort of get closer to telling you guys what the transpose operation is. So, but first, before I do that, I want to tell you how to go from reverse differentiation at least to forward differentiation. And so we can do that using using partial reverse differentials, because the forward derivative is just equal to the reverse derivative in the second argument of the reverse derivative. And this formula is actually magical, and it's what Gordon Plotkin originally showed us way back in 2019, and sort of the crux of this whole story of reverse differentiation. Now, to talk about the transpose, I first have to mention quickly, talk about linearity. So a map is dilinear if, when I take its derivative in that argument, it just gives me back the map. So more explicitly, a map is said to be dilinear in A of j if, when I take its partial derivative in the AJ term, I just get back the map f evaluated at that B argument here, where the AJ part now disappears. In my Levier theory of smooth functions, the dilinear maps correspond precisely to the classical notion of real linear maps. So now with this in mind, I can tell you what a contextual linear dagger is. This is the transpose operator. So normally, if you know a bit about dagger categories, you know that usually you should be able to sort of transpose maps and sort of swap domain and codomain. Well, a contextual linear dagger lets you do that, but only with linear arguments. So a contextual linear dagger is an operation on a Cartesian differential category where if I ever have a map of this type with context on the right and context on the left, and if it's linear in the argument A, then I can swap it. So I have a map. I now obtain a map with context on where the context is untouched, but the B and the A swap places. And this operation is asked to be essentially a dagger. It has to be involutive, it has to be contravariant, and so on and also play well with the product structure. And I'm going to call this map the D-linear transpose. So, now that I've told you that reverse differentiation is how to get forward differentiation, how do you get the transpose? Well, the contextual linear dagger is again defined using partial reverse derivatives. It is literally just the partial reverse derivative evaluated at 0 in the linear argument. So now you know I guess, fundamental theorem of Cartesian reverse differential categories. Okay, but the cool thing is that not only that, the forward derivative and the reverse derivative are transposes of each other. So if I have this dagger operator, then in fact, I can just say that, for example, the reverse derivative is the linear transpose of the forward derivative and vice versa. And not only that, now that we've introduced partial reverse derivatives, well, one has to do a sanity check to check that, yes, our notion of partial reverse derivatives is in fact the linear transpose of the usual notion of partial forward derivatives. And it's true. Hooray. Okay, so now let's get to the Faà di Bruno formula. Yep. So now, so to do so, I'm going to talk about higher order derivatives, and then I have to define higher reverse order derivatives and tell you that, do a sanity check to show that they are indeed transposes of each other. So just because I'm running a bit out of time, the higher order derivatives, your first attempt in defining a higher order derivative would be to apply the differential combinator a bunch of times. And that'll get you something of type a to the n to b. However, there's a lot of redundant information that turns out in this. And it's that, for example, in the second order derivative, you can show that it's actually a sum end of the partial derivative plus the original first order derivative. So it turns out that all you need to really do is talk about differentiating the function f repeatedly in the first argument, in that non-vector argument. So we define the nth higher order forward derivative of f as being the function where it's of type a to the n of b, where you continuously derive the first variable here. And it's defined inductively as follows. And not only that, this function is both n-linear in its last n arguments, multilinear in its last n arguments, and also symmetric. So we want to do the same thing for reverse differentiation. I want to define higher order reverse differentiation. And if you do the same trick, well, first you start applying R, and well, you realize the domain and the codomain start to explode really, really fast. So instead, we sort of do the same trick where we only take, oh, and then once again, you can show that if you do the higher order reverse derivatives, there's a bunch of redundant information in there. So instead, we're going to do the same trick where we only reverse differentiate the non-linear argument, the non-vector argument, over and over and over again. And what you see is that once you do it once, you go from a to b to a times b to a. But now, because you're doing the reverse derivative in this argument, the b is here, and you're not touching it anymore. So then it just becomes a to a, and then you just keep adding on a's, so on and so forth. So the higher order reverse differential is of type a times b times a to the n-1 copies afterwards. And you can define it inductively as such. So we'd like this higher order reverse derivative to be the transpose operator, to be the transpose of the higher order forward derivative. So what we'd like is that, so again, because I'm running out of time, unfortunately, this doesn't happen. I don't know why. I've tried really hard to make this work, but there seems to be an axiom missing. So essentially, this is why we had to introduce what's called the stable rule. So the stable rule was introduced by Aaron and me just to make the fact that the higher order reverse derivative in fact be the transpose of the higher order forward derivative. And essentially what the stable rule says is that if you sort of forward differentiate first and reverse differentiate, you sort of can swap them around. Or you can do, it's the same thing as reverse differentiating twice, because again, you're not introducing more copies of A after you've done it once. And as far as I know, all our examples hold, and I would very much like to be wrong in saying that this is not, that I would like this to be redundant, but I can't prove it using the axioms that we've introduced in our first paper. So potentially the reason why is because we didn't look at higher order reverse derivatives. Anyways, if you've got the stable rule, then you have the fact that the higher order forward derivative is equal to the transpose. Its linear transpose is the higher order reverse derivative. Okay, so just to wrap things up, so here's the higher order forward derivative. And the way that you can do this is that, again, I didn't plan on going into detail on it, but essentially the formula is given by sort of partitions of finite sets. So if you go on Wikipedia, you'll see this super long, complicated formula. And so this is the Faà di Bruno formula in a Cartesian reverse differential category, which is essentially saying that it's the sum of sort of the lower higher order derivatives. So here's And so just to conclude, here is the higher order reverse differential, sorry, the reverse mode Faà di Bruno formula for higher order reverse derivatives. And it turns out that there is in fact, that because if you stare at this formula, you actually do see that there are in fact a bunch of forward derivatives in this formula. And the reason for that is because when you apply the transpose to the Faà di Bruno formula, you're only taking the transpose of one particular linear component while keeping the other linear components untouched. So that's why those forward, higher order forward derivatives are still lurking around. And yeah, just because I ran out of time, I'll leave the formula up here for you guys. Thanks.
If you have time for one question.
Okay, I'll make it quick. I know that in Mortal, the Bell numbers, the Bell polynomial show up in the Faà di Bruno formula. So I'm wondering, is there a sort of categorical analog?
So I will say that this formula, the way it's written here, was by Richard Gardner, and it's already pretty simplified from the original version that Robin and Robert Seeley had originally. The Bell numbers, where'd it go? The Bell numbers would, nope, not here. The Bell numbers would appear here when you try to give expressions of the domain and the codomain for the higher order reverse total derivative. And actually, Aaron did mention this to me, and I went, oh, that's too complicated. I don't like that. But that's where they would appear.
Okay. If you have a short question, we can take one more.
Maybe just mentioned that maps that are like bilinear are not necessarily linear.
Yes.
Do you have any like equations for why that?
Yes. So in the category of smooths, so in a general differential category, they're not the same thing. In most of the examples that people care or that people look at, they are the same thing, but by definition, they're not. And the reason for that is that sometimes differentiation is a stronger thing than just addition. I only have synthetic examples where they're not the same. Maybe Robin has better examples where they are not the same. I'm sure he's smiling at me, so it sounds like he does. But yeah.
Let's thank our speaker again.